do I share slides? Okay. Share slides.
We get it sorted out, Sam. Don't worry.
Is Robert Kuhneman remote?
Sorry?
Is this one remote?
I don't know. I'm busy trying to get Sarah's slides uploaded.
Chris, could you try and join the room from the full client and then do an audio chat?
Sure.
I'm kind of hearing it. There's echo coming from me. That's you, yeah?
That's me. Sorry.
Hey, there's a typo on this slide. My name is missing an F.
Whoa.
Oh, hang on. Oh. Okay, I'll fix that. Sorry about
Of
that.
all the terrible things that can happen.
No, I can't because I've used my other computer to make the slides. I was dumb.
Apologies.
Sorry. I'll fix it after the session. This is why I shouldn't have brought 2 laptops to the IETF.
Okay. So.
I have access.
Can you send audio just to see if it's volume problems?
I can hear it from my computer. Oh.
Hello.
Let's go.
No, that's
Okay.
just Mark.
He sounds fine.
Yeah.
Okay, Mark, I think it's just you with the audio. Okay, we should start anyway.
Mm-hmm.
Okay. Fire ahead.
Okay. Hi, everybody. This is UFMRG, Usable Formal Methods. We've got some interesting presentations for you, but first, this is the note well. Please note it well. It would be really great if everyone could be nice to each other. Our agenda is not completely full, but hopefully we will not have to do my talk, which we have been not doing for several sessions in a row now. So please ask lots of questions. Does anyone have any agenda bashing they'd like to do?
We had, who wanted to move?
Summer. Okay,
Osama, is he gone?
he's gone.
He's gone, okay. So
Okay.
Osama might have to move later, so.
I mean, I put him at penultimate, so.
Oh, okay, you moved already.
Okay, any agenda bashes? No? In which case, I think we're going to go straight to Mark.
Okay. So Mark, we'll give you control of the slides in 1 second, once they're up.
How do I give control?
So if you just choose the peoples, and then for Mark, if you just give him plus there, plus slides.
Bonk. There you go.
Okay, Mark,
Control Mark.
off you go.
All right. So I hope you can hear me well. I'm trying to speak a little bit loudly. So hi, my name is Marc Petit-Huguenin. So the original presentation was 30 minutes long, so I have to shrink it a bit. So I don't know how much time we will have for a question after, but we will see at the end. Okay, sorry, I have to switch between 2 screens. Okay, so this cut, we will go back to it. It will become clear a little bit later in the talk, but I'm going to read it. My faith, for more than 40 years, I have been speaking prose while knowing nothing of it, and I am the most obliged person in the world to you for telling me so. So, the goal of this presentation is to explain the background for an internet draft I wrote, which is about another internet draft. So in 98, Dr. Rivest, the R in RSA, wrote a specification for a variant of symbolic expressions. This specification was formatted as an internet draft, but was never submitted to the IETF. So a few years back, a year or so back, this specification disappeared from the internet. And so we no longer have a way to have a reference to this specification. So with Donald Eastlake, we started to work to publish this specification as an RFC at the IETF. And I was working, I was doing the reviews on the original specification from Dr. Rivest to find all the ambiguity and the contradictions that could be in this specification to publish it. And this is something I'm doing since 20 years, is that I use formal method when I do a review or when I write a new specification from the internet. But the thing is that this work is completely invisible to the IETF, right? Nobody knows that I am doing this. So I thought that this time could be a good idea to show exactly what I do, what formalization and what proof I write for me, to verify that my specification or other people's specification are correct or more correct. So this presentation is more tailored for people from the IETF that are protocol designer and so on. It's less more, it will be less more interesting for people from academia because they already know all these things, right? But this is the kind of presentation that I really wish I would have seen 15 years ago at the IETF and would have brought me sooner in the path of using formal method. This is not an attempt to convince anyone to do the same thing that I do. I don't want that. I just want to show what I use and to let people think for themselves and try to find their own path. There is no one way, just find your own way. So we are going to go progressively through some what proof are, and I'm going to start with pen and paper. No, sorry, I missed a step. Yeah. So first, what is a proof? So a proof is a deductive argument that shows a stated assumption guarantee a conclusion. That's it. There is no more to it. But a proof implies two other things that always come with this. First is a proposition, right? This is a declarative statement, and this can be read as a question you want an answer to, right? So this is very important to start with your proposition, then you have a proof. But there is a third thing which is equally as important, which is a process that verifies that the proof is correct from that proposition, right? You should not trust a single thing that comes from the IETF, and you should not trust, because you should not trust a single thing that comes from the internet, right? You need to read it, to understand it, and to find a proof of it, and then to verify it yourself. And this is exactly what this third step is about. So the oldest kind of proof is pen and paper proof, right? So the proposition is a mix of plain English and mathematical symbols. The proof is a sequence of logical steps that shows that the conclusion of this proposition that gives a conclusion and shows that the conclusion is correct. The verification step is done by peer review, which means that other mathematicians go, read the proposition, read the proof, and by themselves verify that the logical steps are correct. The simplest is to show how it looks. And this is an example of a proof, right? So a pen of paper proof. So this is called a theorem at the top. A theorem is simply a proposition that has a proof. Before a proposition has a proof, it's called a proposition. After you find a proof for it, it's called a theorem. You can find also the name lemma from time to time, but for all intents and purposes, this is exactly the same. You have the proof after this, and one thing to take away from this slide is that there is a lot of things that are unsaid here, right? There is no definition for what a real is. There is no definition for addition, subtraction, multiplication, and so on. So there is a lot of steps that have left because mathematicians, this is to talk with other mathematicians, and they know all these things, so they don't have to repeat all these things each time they do a proof. Now, the problem with pen and paper and proof is that the proofs are becoming more and more complex and bigger each time. Now it's not uncommon to have proofs that are 10 of pages or even hundreds of pages. Who is going to verify this? This is a very costly process, and this is not a very well rewarding process, right? It's great to find a bug or a flaw in someone's reasoning. This is not fun to say, well, it's fine. I just spent 2 months on this for nothing. So proof assistants are a way to use computer to improve on this, right? So here, what happened is that the proposition is encoded in a logic calculus. The proof is encoded into a formal language, which is generally different from the proposition. And then the computer does simply a verification that the proof match is correct for the proposition. This is how Isabelle Tamarin, which are examples we already talked about in this research group, are doing. So some proof assistants are more specialized than others. Tamarin, for example, is specialized for security proofs, which is a subset of all the proofs that are interesting for a system at the IETF. And I want to emphasize a little bit about this, right? It's doing only security proof is like verifying that your entry door is secure, but not verifying that your leak is not leaking, but that your roof is not leaking, right? You certainly need to do both to verify that your house is in good shape. So I am a programmer. I have been programming since 40 years. I have been paid to program for more than 30 years, right? So programming is what I know and what I know very, very well. I am not a mathematician, and I will never be a mathematician. So proof assistants that are based on a lot of maths that you have to learn and you have to understand and you have to internalize is not something that is easy for me. And I would bet that there is more developer at the IETF than there is mathematician at the IETF. So there is a third way beyond pen and paper and proof assistant, which is the Curie-Award equivalence or the Curie-Award isomorphism. So the idea is quite simple, but it's quite brilliant, I would say. The idea is that the type of a programming language can be used to encode a proposition. Right? The same way you use a logic calculus, you can use a type system of a programming language to do that. And then writing code that compile is equivalent of writing a proof that is verified. And that's it. This is a brilliant idea behind Curie-Award equivalence, is that you don't need to learn all this mathematical stuff. You use what you already know. You extend what you already know, which is coding, which is programming, right? And this is a very important stuff because the leap, so there is still a lot to learn, right? But this is a less work than relearning all these things from scratch and perhaps doing a PhD. I don't know. So there is, unfortunately, not all type systems are equivalent, and not all can encode all possible propositions, right? There is a part of the proposition which is called quantification, which cannot be done with the normal type system that you use, even something as sophisticated as Rust, right? So this is why, to do that, we need special type systems, which are called dependently typed system. And there is 5 languages that are in use, and more important that are maintained, which are Coq, Agda, Lean, F-star, and Idris2. So the one I use in this case, and I use since a few years now, is Idris2. This is a programming language which has a very compact syntax, which is inspired by Haskell, and which has a dependent type, so we can encode any proposition in the type system of Idris2. In addition, it has an extension which is called a linear type system, which permits to encode state machine, which is very useful for a place like the IETF when we work on protocol, and protocol are most of the time based on state machines. So this type system permits to encode proposition related to state machine in an easier way and a safer way. Another thing that the reason I choose Idris is that it's pure ASCII. You don't need any Unicode symbol to write Idris code. And it was really useful because this permitted me to embed the type and the proof directly inside my internet draft. And as they are available in the XML file, in the RFC XML file, you can extract the source code and you can verify it. Again, don't trust anything I say. Just go, download the XML file, extract the Idris code, and run it through the Idris compiler, and you will see that it verifies. So what I said, assuming that the Idris compiler do not have bug, should be correct. So going back to the specification. So the internet draft I wrote is specifically about the draft that Dr. Rivers wrote, not about the new draft, right? The first step was to find what are the ambiguity and what are the contradictions in the original document so we can fix it in the new internet draft. So this is exactly what I think and what I explain inside the document. So there is 3 parts for each section of the original document. One that said, okay, there is this ambiguity, this contradiction, and we will solve it this way. The second part is the proposition in Idris that encode exactly what I just said in the paragraph, in the section before. And then I put some proof of correctness for the correct examples. The examples that were in the document, I prove that, yes, they are correct. Some were incorrect. So I plan to do that again when the draft will be close to be published, to verify this time that the ABNF and that the example in the new document, the soon-to-be RFC, are also correct. So a few thoughts about the process of formalization. Formalization is hard, and it's incredibly hard. And there is 2 reasons. One that goes back to what I said with pen and paper. This is a computer. You have to explain everything, right? A computer doesn't know about real number, doesn't know about natural number, doesn't know about string. It knows nothing. And so you have to find someone who already explained something to a computer, or you have to explain it yourself, right? So this is the first step, which is difficult. The hardest part is the fact that when you write a proposition, you have to know everything about the subject you are talking about. And this is the hard part. When you code, especially with not so good language like Python and so on, you don't really have to understand everything you do, right? As long as the test pass and your employer doesn't fire you, then who cares, right? When you write a proposition, you have no choice. You need to understand every single thing. And I had to do I did a formalization last year for the DNS, right? The whole DNS, including DNSSEC. That's 1,300 pages of RFCs. It took me a whole month to write the formalization, only the formalization, no more than this. A whole month to understand everything. And trust me, finding an answer in 1,300 pages of RFC is not simple. So this is a very difficult part, and this should not be underestimated. Now, for the same reason, formalization is good, right? Because you know everything about the subject, right? And you have to first resolve all the ambiguity and contradiction. You can just say, oh, it's just fine. The worst sentence you can hear at the IETF is, oh, don't worry, this is a corner case. No, I worry, this is a corner case, so the million of calls in my case that I make each day will be a problem for a substantial number of people. Knowing everything about the subject at hand is very, very important. And I would say that you don't even need to go to model checking or proof writing and all this stuff. Just do the formalization. You will find an amazing number of bugs just by doing this. All right? So this is very important to do this. For the record, I do not go directly writing proof. And this is similar to something Jonathan said I think it was an interim meeting, is that I sketch things into another language. In fact, I use Petrinet to sketch what I want to do to verify more or less that things are working before doing this. And using that Petrinet is a thing that helps a lot. I am currently designing a new distributed protocol that I plan to submit to the IETF, and you have no idea how many bugs I find each day that I have to fix in the protocol thanks to this kind of formalization. And the last thing, this is my last slide, is that formalization is useful. You already encoded your protocol, your specification in a programming language. So now you can derive things, right? You can write program to extract information and generate other stuff. I use it to generate a BNF automatically, right? I don't need to write the BNF by hand. And I certainly don't need to format it by hand. This is a program that is doing that. Diagram generation, same thing, right? State diagram. You don't need to draw a state diagram. You just let the system draw it for you from your type, from your specification. I do that with another thing, which is a specified test oracle, which is a piece of code where the programmer can put an input. The test oracle gives the correct input, and then the programmer can compare it to their own code, right? And the next step is automatic testing, where I have a generator of all the possible input for the system, and I use that to test the code of the developer automatically in a bunch of servers to find bugs automatically without having to write a single unit test. They are generated, and they are applied automatically for me. And this is the end of my presentation. I hope you have questions. Again, if you don't have time, we will find.
Okay. Any questions for the speaker? While people are thinking of some interesting questions, I think this is very interesting because Sam Scott, when he was doing an analysis of Tamarin, did something very, very similar, although much less formal. I just posted a link in the chat where he literally had a whole page of the spec on one side and how a description of how it was modeled on the other side. And you get this very, yeah, I don't know if I can share it easily, but you get this very, very nice formalism. And so doing it inline definitely sounds like a good approach. Chris P.
Yeah, thanks very much for the talk. I just want to ask a really high level question. What does usability mean to you? Like what's the usability problem here that's being solved?
All right. So, and I said this multiple times, usability is in the eye of the beholder. Right? What I find usable, someone else will not find usable. I don't find Tamarin usable at all, right? But this is because I was not trained in this kind of things. I find Idris and the idea of the Curie-Award isomorphism usable. Why? Because I am a programmer who thought a lot about type in his career, right? So I believe that, well, I think that for developers, and as I said, there is more developers than mathematicians at the IETF, Curie-Howard isomorphism could have a slight edge over other way of doing proof and formal method just for this reason. So this is what I meant by an usable formal method for specifications.
Dimitri?
Dmitry Izumsky, Intuit. So I have a question mostly like, say currently we're starting to work on some security RFCs, and question like for this part, like what is starting point, like how to make this specification friendly for formal proof from beginning? Like what practical steps here?
For a specification?
Yeah, like if you start with new specification, how make it more provable from beginning?
Well, so an interesting thing is that if you do the kind of things I did for symbolic expression, is that the way you do your formalization change the shape of your specification, right? Is that you have more logical step. So it's a good thing. So I have to explain something. I certainly didn't have enough time to explain all the things I do, but I use something which is called literate programming, right? And in fact, the Idris code that you saw is mixed inside the text of my internet draft, right? And when I write an internet draft, I have the specification, the formal specification, right at the same time that I write the internet draft. And there is a piece of code, piece of text, piece of code, piece of text, and the code is the formalization of the text, which is just above. Idris has this thing that it doesn't do easily forward reference, backward reference. So you have to order your Idris code bottom up, right? You have to start from the bottom. And I found that if you do that, it gives you a nice organization for your code, logical for your text, logical organization to organize your specification. Now there is a second thing. This was a one shot, what I did to show the formalization behind. But what I wanted to do is to show that it's possible without any GitHub separate anything outside to publish the specification in a separate draft, but also to publish entirely in a draft. And I think that this is something I may or may not do in the future to show, well, here how I guarantee that the thing I said in this other internal draft are correct. Does that answer your question?
Daniel.
Hi, this is Daniel Smallin speaking. So one thing that I've observed in formal verification, especially the languages that you mentioned, environments maybe is a better word, is that they seem to excel at creating proofs around things like cryptographic primitives and sort of things that for many folks in software engineering they might call those as low-level abstractions. And there doesn't seem to be a strong way to connect this to higher level abstractions. So for example, there are formal ways of modeling things like architectural description languages, where you're really not reasoning about primitive types, but maybe you're reasoning about overall properties of the system, quality attributes, and so on. Now, this is sort of a two-parter question. I guess the first part is, have you ever encountered any problems where this lack of an interconnection in these modeling types has come in the way of you doing your work? And then the second part is, do you see then there being any kind of benefit to having some sort of a solution to bridge this gap or not?
Yes, definitively. My day job is software architect, specialized in distributed system, right? So this is the kind of things. And what I no longer write code because I'm apparently too expensive for that, but not code that goes in production at least. What I write is code to prove that an architecture is working, an architecture is correct, and things like this. It's difficult. I mean, there is not a lot of guidance. There is not a lot. You cannot find a lot of books that explain how to do this. There is a few. If you look at the domain domain-driven design. It goes in the right direction. This is not exactly that, but there is already a lot of tools that permit to do that. But yes, definitively you can use this kind of tools, but you have to be creative, and you don't want to put you in a place where you know so well a tool which is not adapted to what you want that you cannot see how to do other things. You really need to see a lot of different systems, a lot of different language, and so on, to find the ones that really can solve the problem you are working on.
Thank you.
I would just say that there are definitely tools that are higher level, right? If you think of like Tamarin, is completely abstract and doesn't do anything to do with code. It's a totally different shape.
Okay.
Yes, and by the way, Idris is abstract. A thing I didn't say is that, and this is a thing which is very surprising for a programmer like me, is that you don't run the code that you write, right? Running the code has no meaning at all. Oh, it runs, so what? No. The thing is in the compilation. This is a compilation that gives you the answer you want. This is not running the code, right? So, but you can run the code. The same way that in Tamarin you can extract code, right? This is the same idea. You can extract code, but this is not the point. The point is to show that your proposition can be implemented, does not loop, does all the properties that you want, and you don't. So this is still high level, and you need to go lower level. So there was a paper published last December, I think, by the people from F-Star, which shows how to match these high-level things with the format, the format of a PDU, right? The format of the data which is sent, and how to verify this. This is a very interesting way to link the high level and the low level.
Great. Thanks, Mark. So I guess we'll move on to our next speaker.
Right. Thanks.
Thank you. So Ben.
Okay, yeah, let me give you control of the slides.
Okay, well, good morning, everyone. My name is Ben Greenman. I'm an assistant professor at the University of Utah, and this is joint work with folks at Brown. We have Shriram Krishnamurthy and Tim Nelson, and the all-star PhD student, Siddhartha Prasad. All right, and I can control the slides. So Forge is a tool for debugging your designs. You, the programmer, start off by describing what data types do you have in mind for your system, and then you write down relationships between those data types or constraints. And you do this all in a language which is basically a scripting language for set theory. Then Forge spins its wheels, and you get two modes of use out of this tool. One is you can explore the data types that you've created and see what consequences they have. And then second, you get bounded verification. So you write down conjectures in Forge, and you can verify whether or not those hold, up to limited bounds. So let's look at an example to see how Forge works. And we're going to go way back to the 1990s and talk about cross-site request forgery. So what's happening here? We've got a user who loads up a web page, and this user wants to make requests to a good server over on the right. We can get into trouble here because the web page is going to forward authorization cookies to any request that comes from the web page. So those will all go along to the good server. So if we have an evil server which provided the page, or an evil server that did a cross-site scripting attack and is able to make requests via the web page, both of those requests at the end at the good server are going to have the same cookies inside. So we could wind up with something like I'm talking to Netflix to order a DVD to my house, and the evil server has sent in a request to change the address. So now the DVDs go to another place, not to me. So this is a problem. What can we do to fix it? Here's an idea. Let's add an origin to every request. So scripts that were provided by the evil server will now have an origin that says I came from an evil place, and the good server can check these origins and make sure that they match up with where the request actually came from. That seems like a plausible idea, so let's try it out. Let's model that in Forge. We start off with our data types. So we have an abstract signature that says we have endpoints. Endpoint is like an object. Right now it's just an opaque thing. There's no members inside of endpoint. One type of endpoint is a client. Client is also just a black box. The other type of endpoint is a server. Server has a set of causes that come with it. So these are things, causes here is our source of truth. So every request and response later on that was a consequence of what the server has done is going to show up in our ground truth set clauses. And then we need a few more data types. So here's just a sketch to show what's happening with the rest of them. We have an abstract signature for HTTP events, and there's 3 kinds of events down below: request, response, and redirect. Every HTTP event has one endpoint that it's from, one endpoint that it's going to, and one origin, which is the new thing that we've just added. So the really cool thing here is just by describing these data types in a few lines of code, and this is all the code that you need for these data types, we can immediately start using Forge to explore what are some instances of the data. So down at the bottom of this slide, you can barely read it, but it says, explore for 2 servers and 1 client. What are possible configurations of endpoints? So you can immediately get a sense of what data examples does this code give us. Next. Now, part 2, we need to talk about the relationships between these data types. So here's one predicate to give you a taste of that. And the relations typically come in 2 flavors. So type 1 here is facts about the world. So one thing we want to know is every response should be paired with a unique request. Every request has a field inside, which says here's the response. And what this predicate is doing is make sure that these things are one-to-one. We don't have 2 responses to the same request. Response shouldn't be doing double duty like that. The other type of predicates that we need are facts about the design that we're experimenting with. So we're interested in good servers that enforce origins. This predicate is saying, well, a server is good if, for all requests that come in, if that request is headed to the good server, then one of the 2 things below need to hold. Either that request has originated at the good server, or that request has an origin that matches where it's coming from. And in this case, it's going to be a request from the client. So what we don't want is a mismatch between origin and from, where the evil server has gotten something in that looks like it's coming from the client. So those are 2 predicates. We do need a few more for this model, but I'm going to skip over those. And now we can finally test a conjecture. So we have a run command, which would show up at the very bottom of our Forge file, which says, can we find some good and bad server where the good server is enforcing origins such that we get into a bad scenario where request is mismatched. And we'll explore this up to some bounds that we specify. And the idea is you start off with small bounds and work your way up to build confidence that this property has no counterexamples for a larger system. But usually you can find the hypothesis is that you typically find a counterexample within small bounds. And Forge has found a counterexample to our conjecture. So we would hope that there's no instances where we can get a mismatch. And here it's showing, well, this is one where it can appear. And just like before, we have a directed graph to describe the instance. So this comes out of the box from Forge. Excellent. So we took our idea, we sketched it out in a few lines of code. We found that this idea has a flaw. And now we can go back to the drawing board and say, okay, well, maybe we need to reconsider this design. What can we do to make sure that we have no evil servers sneaking in requests? One idea that comes to mind is to add a set of origins. Because the basic problem here is that when we have redirects mixed in, we can get things that are mislabeled. But the takeaway message here is with a little bit of coding in Forge, we were quickly able to find a bug. So this is a much better way than just working on pen and paper and testing out examples by hand. Let's step back for a bit. Forge sits in the space that we call the lightweight formal methods arena. And there's several tools in this domain. Lightweight FM, that name comes from an older article by Daniel Jackson and Jeanette Wing. They have a great line in that article which says, the cost of a formal proof is typically an order of magnitude above the cost of a specification. And the cost of a specification alone is often outside the budget of a real project. And at IETF, that's absolutely true because everyone's a volunteer, so there's no budget. So we're lucky if we can get a specification. So Lightweight FM is trying to sit between this rock wall of proof assistance where you get very high assurance, but you also have to put in a lot of effort. And we're also trying to navigate past the whirlpool of model checkers where you're at the whims of an automated algorithm, which is going to explore a huge space, but it may take a very long time to get back to you. But of course, there's a trade-off here. So all these tools work, Lightweight FM, by sacrificing completeness at full verification in exchange for usability. And I touched on this briefly before. The hypothesis at play here is that most bugs are going to have small counterexamples. We should be able to find an instance which explains a problem without going too deep into the universe. There shouldn't be too big of a world where this bug shows up. You know, and there might still be a bug. Maybe that's the way you bring in the proof assistant later on. But to build confidence at the start, this is a great lightweight way to make progress using formal methods. Okay, so Forge is one of many tools in this lightweight FM space. What sets it apart? There's 3 things that we've been working on: custom visualizations, support for unit testing, and language levels. Visualization is just a no-brainer. We saw some directed graphs before. Those come out automatically out of the box, which is very cool, but they are tough to understand. So the picture at the top and the picture at the bottom are both visualizations of the same instance that came out of the solver. The top one has a lot of theming and styling to make it more readable, and it's still completely incomprehensible. So this example is from a different paper related to Forge. We're modeling a cryptographic protocol. This is Needham-Schroeder with a vulnerability. And the picture at the bottom, it's like anyone's guess what this is saying. And the picture at the bottom says, okay, well, here's a sequence diagram. We've got an attacker sitting in the middle, and you read the text and you see, okay, the attacker has access to the public key. This is a vulnerability. Custom visualization works because we have the visualizer is plugged into modern web frameworks. So you open up a browser tab, you have 3 columns here. One is the viz on the left, the middle is JavaScript code that you're in full control of to write, and then the right-hand side is a browser to show you what objects do you have at play from the solver that you can work with inside the visualization. This is an area for improvement, okay? We have the full power of JavaScript, but we also have, the total unconstraints of JavaScript. So we're working on building more of a standard library to help make common case visualizations easier to build. But just the fact of having this, I think, is a huge step above the directed graph. And right, it's more than pretty pictures at play here. Understanding these counterexamples is critical to making progress and actually using formal methods. And we're building on research in cognitive science here. And this is a paper from UPSLA a few years ago, where we were doing user studies to find out what instances are most effective to helping users of a formal tool make sense of the examples that come out. Second, unit testing. How do we know that the model we've built is correct? The models only take a few lines of code, but it's very subtle lines of code. At Brown, we've been using this Forge tool to get students who have no interest in formal methods using it to debug their designs. Part of what we need to do is build on experience that people have from Java and unit testing or whichever, and get them to be effective modelers. The real challenge we're facing, though, is programming is a completely different activity than formal modeling. So programming is more like the situation on the left, where we've got a robot and we're telling it step by step, you proceed through this world. After time step 3, you take a turn to the left. There's a sequence of instructions, and that's why things like printf debugging make sense in the programming world. It doesn't make sense at all in the modeling world. We're more like the person constructing the vase here on the right, and then the solver is filling in the blue liquid to say, well, here's what interesting shapes can come out given the domain that you've described to me. So one of the constructs we have for testing is assert that was on the previous slide. Assert in Forge is totally different than an assert in a programming language. It's more about comparing 2 predicates. I assert that predicate 1 is an over constraint of predicate 2, or I assert vice versa, that we have an under constraint, and you use these to hone in on the property that you're ultimately interested in. Third, language levels. Again, we have a rich modeling language, scripting language for set theory, and it's very tricky. What is this line of code saying? It'd take me a minute to unpack it for sure. And if we have a student who's coming in who only knows Java, it's like, well, I have no idea what's going on. This is just a non-starter. We use surveys to introduce different levels of languages that we have to students. Okay, so going from step 1 to step 2, this is one of the questions on the survey. What does this mean that we say the course CS1 is in the set of prerequisites.cs2? And one of the student responses was, I hope that Forge doesn't allow me to say the thing in the code here, because that would be a total travesty. Like method.object, this makes no sense. So we need to have these different levels. We start off with a small contained language, which is only functional relations, and then we can totally use this Java analogy. There's SIGs describe objects, objects have methods, and there's no going backwards. You don't have relational join yet. Then step 2, we can talk about relational algebra and introduce n-area relations. And then step 3, we had linear temporal logic, or LTL. And the point is, each one of these languages is expressive enough to do some interesting modeling work. And you can only go so badly when you get something wrong and have an error message. You don't need to understand the full language at once to make sense of the errors. Let's zoom in for a minute on the third level language, temporal, because we've been doing a lot of work recently to understand LTL and LTL misconceptions. So this has been multiple years of studies with surveys and talk aloud interviews. Find out where do people go wrong when they think that they have a correct LTL specification and it actually has a subtle bug. So right now we have a code book of several different types of errors that show up in LTL. I'm going to skip through this here, but this is a little quiz. We can talk about it afterwards during the question period, but it's one example of a misconception error. So how do we turn this into LTL? The green light is on exactly once. And you can do it with just these 3 operators: eventually, always, and next state. Here's a wrong way of expressing it, but it's very close to correct. What's missing is a G on the right-hand side. So what might be going on here is an implicit G misconception. And we've seen surprisingly many instances of this implicit G. But this is one of the things that comes out of the user study. The more exciting thing is we've built these into a tutoring tool. So if you go to this URL, ltltutor.xyz, it'll spin up exercises for you based on what we found, and it will suggest new exercises based on your performance on the ones that you've done so far. So here's a question. Does this formula match this trace? You answer yes or no. And let's suppose we get the wrong answer here. The tool will give feedback in as far as it can to say, well, your property, here's why that's the wrong answer. Okay, so we've seen Forge. It's a lightweight modeling tool. It takes in a description of data types, relationships between them, and gives you out 2 modes of use: quick exploration and bounded verification. And then the 3 research thrusts that make Forge usable are custom visualization, unit testing, and language levels. Everything I've shown so far is based on running code, but each of these 3 pillars is also an active research area for us. So I mentioned the JavaScript toolkit. The other 2 pillars are also things that we're actively researching. So we would love to find applications and collaborations in the IETF space to help build this out. Find out, well, where does Forge need to improve to become a better lightweight tool for professionals? There's the Forge website so that you can look it up and please share with your colleagues. And then there's my email address if you want to share half-baked ideas or things that don't fit on the mailing list. Thank you.
Okay. Chris.
Yeah, what a great presentation, especially for this group. I mean, it's like all of the, like this is a tool, this is how we think of usability, but also this is how we like evaluated whether this tool was useful. I guess it's like kind of easier because you just have like a captive audience of students to do experiments with. That's really cool. I wanted to ask, okay, so I'm not a formal methods person and I'm seeing all of these like languages being developed for expressing property, like symbolic properties of things. I'm curious why we don't start with like a programming language people already use. So if like you have students using Java, can we like constrain the semantics of Java, maybe take a subset of the language that at least so like syntactically, they don't have to learn anything new.
Yeah, so that's actually where we're trying to end up is so syntactically you don't need to learn much new. The reason you don't want to verify your Java program is the state space explosion problem.
Can you explain that a little bit?
Yeah, a program says a lot. There's a ton of details in a program about what needs to happen at each step. And for a model check to go through and verify that, you've got to find some way of breaking it up. Otherwise, there's just a huge space of possible states that the solver needs to deal with. And then you don't get an answer in time.
Okay, thank you.
Yeah, so constraining things to data types and relations is a way of cutting down on the state space.
Donna.
Okay, sorry. Alice Woodman. Can you compare this with things like Quick Check, some of the other things like Coq and things that come out of the pure functional programming space, the Haskell corner.
Sure. Any others?
No, I could give a longer list, but I mean, I think you understand the corner. So
Okay.
what
Yeah.
do you-
So Coq and Idris from the last presentation, these I would say are in the proof assistant space, where you get very little automation to help you prove a property. But on the other hand, you can get full verification in Coq, right? So you completely know that this theorem is satisfied once you've built a Coq proof. A quick check, on the other hand, is a very lightweight tool. Quick check, you specify tests as properties. So instead of constructing the full input for what I want to test, I say, well, here's a property that all my input-output things should hold. Property that should be true of all inputs and outputs. And then quick check will automatically generate the inputs for you. So in that sense, quick check is similar to the exploration that Forge provides. Quick check comes with these generators for different data types. Like quick check in Haskell, it would be Haskell data types. We can construct instances in quick check. And the difference is the property language in quick check is just the Haskell language. So you've got a general purpose programming language, and it can explore things in that given the time you've given it. And we have a more abstract state space in Forge. So hopefully we get further and we have higher assurance that the property is true than the pointwise checking that you get in quick check. Yeah, I think of these things as on a continuum. So quick check is like the lower end of formal methods, lower quality verification. And then Forge is a step above that. And then proof assistant is a huge step above that.
Okay, thank you.
Someone?
So that actually, I've now changed my question. That was very interesting because I was thinking on what you said with most proofs have most counterexamples have small instances. So one of the things we found when we were doing TLS 1.3 was actually quite a big instance with like 3 handshakes and 18 modes, and it broke. And so if you would actually want a proof, you have to do the full thing anyway. And I was thinking, well, I definitely wouldn't want to do something in one language, only to have to throw it all away and start again in a bigger language. But is there a way that we could stitch the two together and just be like, we're doing it in this like very small subset, and then when I'm ready to do my full proof, I just like turn it onto like sport mode, and it just like, I don't know.
Yeah, that really would be ideal. I think that's where we need to end up. But where we are now is there's this huge gap between like designing something on a whiteboard and then getting that initial prototype. And Forge is trying to fill in that space where it's something just above the whiteboard, and I can find many bugs. You know, the devil is really in the details of that word. What is most bugs? It could be 51%. But.
Colin.
Hi, Colin Perkins. So I am very much not a formal methods person, but looking at watching your presentation, it struck me that this language seems to be quite declarative, and a lot of these modeling languages seem to be quite declarative in style. The way we write implementations of the protocols tend to be very imperative. And this whole set of actions to perform in what order and so on. And the way we write RFCs tends to be very imperative. And there seems to be this sort of disconnect between the way a lot of people think about writing the specifications and the RFCs in the IETF and the way the people writing the modeling languages think about modeling them. And I'm not quite sure where I'm going with this, but it seems that that disconnect might be part of the reason why people struggle with these sorts of tools.
No, it could be, and I really appreciate the observation. What I would ask is if you find a point in the specification or something stands out to you, like maybe this could benefit from a Forge model, then send a ping to the mailing list or send a ping to me. So, I mean, we're happy to go through and do some of the work in modeling, and maybe that can help close the gap as we move forward.
Yeah, thank you.
Did you join the queue, Felix? You changed your mind. Okay. In which case, should we thank the speaker?
Thanks,
And,
Ben.
We'll move to Mohammed. And this is where you're probably supposed to put the slides in order.
Yeah, don't worry about the order.
Which one? Which one's your slides?
Formal analysis.
It says number 1. Oh, okay. Well, hang on. Do you want to drive the slides or should I?
You are.
If you could do it, that would be great.
No problem.
All right. Hello, everyone. I'm Sama from TU Dresden, and this is joint work with Arto Nemi, Hannes, and Thomas Fossati, who might be familiar to you. They have been very active in the IETF already. Around a year ago, there was a call for formal analysis of a tested TLS draft, which they had already been working on, and I volunteered for one of the formal verification task. And I would like to thank also Confidential Computing Consortium, who actually funded me to be here. Next, please. So the agenda is that I will talk about the background of what this attested TLS is all about, just very quickly, assuming that you folks are familiar with TLS. And then I will describe what the formal analysis goal was and what was the approach that we took, tools that we used, what were the challenges around in this domain, and how we validated TLS 1.3, which was actually claimed in the S&P paper to be validated, but actually was not fully validated. And then formal analysis of attested TLS, which we are currently also doing. So it's an ongoing process. It's a long thing to be verified, and I will summarize and look forward to your feedback on this. Next, please. TLS is very good for network security. We have formally verified it many years ago with all the tools that we have: symbolic security analysis, cryptographic analysis, computational analysis, and all that, handwritten proofs and all that. It's very good. Next, please. But it's not good for endpoint security. So that means basically if the endpoint is compromised, all the security is gone. So we have done all the nice proofs and all that. But what if the key was actually key with which the server or the client was authenticating? That actually key is compromised. Next, please. And what if the next again? So what if the software actually is compromised itself, the TLS stack which we are talking about? So what if that part is actually compromised? So what it's actually saying is that, hey, the network adversary in between cannot compromise, but all the guarantees are only coming from that the software and the key was actually protected. And not only that, next, please. The platform itself, the hardware that underneath which was actually running that software, what if there were vulnerabilities in that hardware? So none of this is actually captured by the TLS standard 1.3. Next, please. The use case here is basically a very strong one, which is the confidential computing, and that's why Confidential Computing Consortium is funding me here. So that the use case we have here is we actually need, there is some workload running on the cloud, for instance, and how do we actually get to know that this is my cloud to which I will send over my secrets? And that's where all of these three things, the keys, the software, the platform that I mentioned actually is required to be attested. So I understand there are people who are really against the attestation thing and all that, privacy concerns and all these things. So I will not go into that debate, but the thing is that confidential computing actually needs this thing. So that's actually a requirement. And there are solutions already being used for many years because it's a fundamental, attestation is a fundamental enabler of that thing. Next, please. So I will give you a key idea of the remote attestation. There is RFC 9334, which talks about all that. Unfortunately, it actually misses the key idea of that. It has like 56 or something pages about all that, but it does not really clarify the three things, the main key idea of that whole thing, which is that we have three steps or three main things which we need to clarify. And a tester, so following the terminology there, so is the device which is under test. In this case, so for instance, I have the workload running on the cloud. So that is my attester now. I, as a user of that cloud, I need some guarantees that, hey, this is my workload. I am only providing the data to my workload and not to someone else, not to the cloud provider and so on. The other party shown here, the verifying relying party, is the one who is the, in simple words, the verifier. So when I use the simple verifier, the RATS architecture, people from RATS will start yelling at me. So this is just to fulfill that requirement that it's not only a verifier, it's also a relying party there. The key idea is that it will, the attester, which was the entity under test, is generating an evidence. Somehow it has to transmit over to the verifying relying party, and then the verifying relying party will appraise that. Appraisal, just a fancy word for verification. So it will verify that whatever I wanted, the key actually which I wanted is protected, the software is protected, the hardware underneath or the platform underneath is actually protected, has the right measurements, the firmware and all. Everything is actually then protected. Whatever it was expecting, whatever versions it was expecting are up to date, have no vulnerabilities inside. So next, please. And next again, I think I'm just showing that attest and next again. So yeah, so it's just showing the 3 steps, the 3 key ideas of that, that RFC does not really clarify that what the actual thing is. Next, please. So having seen the TLS and RFC, sorry, the RATS architecture, how do we actually combine the 2 things? So that was what the actual proposal was describing, the the starting point where we started. So I had a look at the other domains and other solutions in the design space, what other people are doing other than confidential computing, also like other general solutions. And there are 3 ways in which we can actually now combine TLS with remote attestation. The first one shown at the top, the pre-handshake attestation, and then intra, and then post-handshake. Next, please. I have a picture which describes nicely, which is saying from the remote attestation part, we have important step is collection of the claims. I assume that basically the claims are collected at the right point in time, so we have no freshness issues there, and they are actually protected by the hardware. The only thing then left over is the cryptographic protection. I assume the protection here is provided by the signing of these claims, which is shown here as a signature of evidence. So where in time that actually happens is really important, not only from security perspective, but also from performance perspective. So these are the designs. This you can think of it as the design space, what I can do with all of these options. Okay, so if I do the signing before the TLS handshake has started, which is the first option, in that case, I will call it pre-handshake attestation. That is, before the handshake had started, I have already done that generation of evidence, the first step on the last slide. Then if I do it within the TLS handshake, meaning that more precisely in the authentication phase, that will be the intra-handshake attestation. And finally, if at the end of the TLS handshake, I do that signing, that will be the post-handshake attestation. And as I said, each of them have their own properties. And next, please. So the solution for confidential computing consortium is a very popular solution. That's Intel's RATLS. Almost, I think 90% of the solutions are actually using some variant of that solution. And that's where we actually started with it because the draft at that point in time was still being matured. There were many things which were unclear and so on. And we started with this thing to see, explore the whole design space. And our, or me volunteering was that I had worked a lot with the remote attestation before. I had formalized different options of confidential computing solutions, Intel SGX, TDX, and so on. So different technologies. And my hope was that TLS artifacts are already available. I will just plug in the 2 things and everything will work. So as I said, it's been used in Grameen, RATS TLS, and many other solutions. Open Enclave is by Microsoft, SGX SDK is by Intel, and so on, other solutions. Next, please. Okay, so with this background, so now the goal is to formally verify, next please, formally verify the security of RATLS, which is the most commonly used solution in confidential computing. Next, please. And now I will talk a little bit about the approach. Next, please. Approach is simply, I'm using the symbolic security analysis as defined in the SOK. Next, please. And the tool I have used is ProVerif. It has a nice logo, which is here. And next, please. So the approach looks like this. We have specifications coming from, in this case, Intel had a white paper, specifications coming from there. We have, from that, we created a formal model, just like a typical any analysis, nothing fancy here. So we have security properties. There were no description whatsoever of what it is supposed to provide. So we thought on our own about what could be interesting. I will show you later on. And then the validator process is really important. That's something that I will emphasize later on as well. We do the formal analysis, we get either a proof or attack. So that's a simple process, which we all know. Next, please. So what were the challenges in doing all that? So starting with that, I told this, so this is the reference for the white paper that Intel has since 2018. As I said, it's being widely used all over the place with different variants, all originating from this. The issue was that they had incomplete specifications and outdated specifications. TLS 1.3 is a standard since 2018, and this white paper came out in 2018, but they didn't really update it even until now up to TLS 1.3. The specifications still are in TLS 1.2. That was one of the issues. That's why I say outdated and incomplete, that nothing is really clear what exactly is being done and in which order and how precisely. So we used the community input as well as the implementation, which was available in case of Intel RATLS, to fill all the gaps. Next, please. These two are the, it didn't work. Maybe next, please.
Didn't move?
Ah, okay, yeah, thanks. So this is the figure from the white paper, TLS 1.2 handshake. This is where they show, even in the white paper, not only that it's based on 1.2, they even actually do not show how remote attestation was injected. So the left figure actually shows about attestation, how it all works. The right figure shows about TLS. They never actually show how the two integrate together. And the funny thing is that they label it, the title paper, as integrating remote attestation with TLS, and the paper is never describing what actually, how exactly are they actually integrated together. Next, please. So challenges from the formal perspective and coming to the usability perspective. There were very few comments in the India's TLS formal model for TLS. Next, please. Which actually means that there were literally no comments in the main processes. TLS 1.2, like clients 1.2, server 1.2, TLS 1.3, client server 1.3, and so on. So other processes, even the queries, like they had no comments at all. So how is one really supposed to actually use these artifacts in one's own research work if they are not commented? So we talk about formal methods, we are improving the quality of the software and so on, but we really forget when we actually write the artifacts that we really have to be also following all the software practices. So next, please. So for this, what we did is we have added extensive comments on that. So following all our discussions. Next, please. And the proposal from our side is that ACM has nice badges. One of them is the reusable badge, which includes that how reusable that piece of code is. So we suggest that the conferences should be adopting that more and more. And any one of you who has impact on these conferences is very welcome to initiate this idea. And if you have other proposals, of course, we are welcome to discuss that. Next, please. So there was incomplete validation of draft 20 artifacts. Next, please. As a fix, what we did is we designed a very simple validation framework. Next, please. And thirdly, a simple extension of attestation to that TLS artifact made it running for 1 month. And we couldn't get any idea of what exactly is going on. To give you a reference for that, on my laptop, it used to work in 5 minutes. The TLS artifacts they give the results. And this was really surprising when it was running for 1 day and so on. And then I put it on the high-end server. That's the Ice Lake machine, which the fastest server we have. And even on that server for 1 month, it couldn't give any results. Next, please. So we submitted it to the ProVerif developers to have an analysis of this, to give some idea about what is going on. We never heard back. They were busy. Next, please. So as a fix, what we had to do was just to build it from scratch, all from real scratch. Yes, next, please. So the approach looks like this. We have the community input at the top now, which is part of the formal model. That is, we had a discussion with a lot of people. I will come back to this point a bit late. And then all the things are pretty much standard, except that we have the validation sanity checks, which we added to see that the formal model actually works. Next, please. So with this, I will talk a little bit about the validation, how we did the validation, very simple framework. Next, please. So the key idea is that we have TLS artifacts, or the India artifacts, on the right, and then TLS 1.3 specifications 8446 on the left. What we do is we make a corresponding from our reading the artifacts for that from the TLS specifications, how exactly each key should be derived. And then we simply compare each and every key. For instance, the master key coming from the left and the master key coming from the India's artifacts, and then we simply compare the two. And then if it is equal comparison, so if they are the same, we send a success, let's say output on that channel between the two parties. If not, then we send over a failure. So very simple framework just to see that what's going on. Next, please. And even with this simple framework, we see that there is a lot of failures going on. So we explored it further. Next, please. And this is one of the issues why they fail. We have on the left derived secret shown by the TLS 1.3 specifications that takes as input the handshake secret label, which is shown here L5. So that's the label which comes from the standard, and empty string, which is shown here as a 0. And then that becomes a salt for that. And the input key material IKM shown also as a 0 empty string. And then that derives a master secret. But India's artifact had actually used the handshake secret directly as an input of the HKDF extract to derive the master secret. And that's why it led to a failure in that case. But this was somehow, sorry, and this was somehow surprising for us that this stage actually occurs 2 times in the TLS hierarchy. And in the other stage, they have actually followed it correctly. And this was very surprising for us to see why there is a difference between the two. We kept exploring it. Next slide, please. The first very thought was that, okay, so they have applied formal abstractions, as is very common in the community, that, okay, so we abstract it out, that this might help us in gaining some time. That's the only benefit one might get. But we ruled this out because we explored the original version, and the 3 issues that we found all combined together and individually, we found there was no significant difference in the verification time by eliminating that or by adding that in 2 different versions of ProVerif. Next, please. Okay, an interesting tale of community input. The community input that I had in the approach above there, we contacted the paper authors. Next, please, Bruno Blanchet. We asked him, hey, there was this paper that you had, and we found that this was not as we expected it to be. He said, I was not the one who was coding, so contact the other ones. So next, please, we contacted Karthik. He was on long leaves and is still on long leaves from India. At that point in time, it was for 1 year. Now it's another year. He has a startup. Next, please. So we contacted the third author, Nadeem, who never responded to us. Next, please. So then we thought, okay, so what's the next step? So we checked the repo that we had for TLS, which is public, the India repo, and we saw the people who have actually also used these artifacts in their own work. And then we found one of the works was the Lurk authors, and we contacted them. Hey, there is a problem in the artifacts. We don't think that is actually correct. So this handshake secret and the master secret should not be the way that they are there. Next, please. So so what they said is, we have no idea. If you find out something, please let us know as well. And then we went over to the TLS working group. Hey, there is a problem in the artifacts. Does someone has any idea about this? Why this key is being derived not as per the specifications? I think there was Hugo Krocek who said that, look at this paper of SNP. This is describing exactly how this is being done. I said, yes, we have looked at that. There was no follow-up. Next, please. Then we contacted our nice chairs. They had no opinion on this as well. Next, please.
Oh, I have opinions.
Next, please. So we contacted the CCC Attestation SIG, as I mentioned, Confidential Computing Consortium, who has people from Microsoft, Google, and all the nice fancy things. And they also had no opinion on that. Next, please. And so on. Long story short, next, please. In the IETF 119 hackathon, we had a discussion over this. Next, please. In the crypto forum research group at the IETF 119, we again had a discussion over this, that, hey, this is something that we do not understand. Maybe some cryptographer, by the way, I'm not a cryptographer, so I'm not saying that we were exactly right. So I'm saying that we were just honestly curious about understanding what exactly is the difference between the two. So it's maybe, so in our whole attested TLS team, including ARM, Linaro, and so on, everyone, so there was no cryptographer involved. So we were sincerely interested in really knowing what exactly is the problem. So crypto forum, so we had no feedback except that it might be that the draft 20 artifacts which they were based on might not be the final version. They might not have done it, but everyone was exactly using these artifacts who were extending that, because nobody will use draft 18 when draft 20 artifacts are available, right? So that was the problem. Next, please. Finally, at the tool session at GTMFS organized in France, I met Bruno again. I said, yes, I know you were not the one who was coding, but we have a problem here. Let's sit down and fix this and see into it. So we had a discussion, and then we figured out, yes, the India artifacts were actually wrong. And then we fixed that issue and solved it. Next, please. So,
Very dedicated.
okay, so
just a time check. I see you have
yeah,
39 more slides.
Okay.
We don't really have time for 39 more
so
slides.
maybe I skip over to the summary. So we did some formal analysis, which is in the slides. I encourage you to look into it. And this is for the tested TLS. If you click on the formal analysis for tested, it will directly jump you to the.
No,
No,
it's
we're
just
not.
an image.
Okay, you don't have hyperlinks. Okay, so
Okay, give me a
Scroll
second.
to the bottom.
That's no fun. Okay, we're going to scroll on the bottom. You have...
So we did some formal analysis. We found that they are vulnerable to replay attacks, and I will then just describe the summary a little bit. Yes, thank you very much. So we found that it's vulnerable to replay attacks. The evidence actually is generated before the handshake has even started, pre-handshake solution, and they provide no guarantees for that freshness. Next, please. So there is actually a need for standardized and formally verified or tested TLS, not only from the IETF perspective, the draft being going from a real application perspective, because confidential computing actually needs this kind of solution. Next, please. So the questions for discussion that I had, next please, are number one, is there really a practical attack? And I do not mean the theoretical one that the cryptographers talk about, hey, there is a, if this happens and this happens, then that they can collide and so on. Is there really a practical attack if that derived secret, which I showed for India artifacts, the mismatch that was there, is there really a practical attack which is possible in that case if that stage was actually really missed in the form analysis? Next, please. And I will come to questions. I have a couple of questions, and then I come to your question, Renard. So, yeah, just a final minute. So, is there a fix for RATLS? This I didn't explain. Next, please. I will skip this part. It needs some. And how to deal with underspecification. Like the RATLS specification that I showed was largely underspecified, and the other solution for post handshake that we are looking into is even more underspecified, that they don't have even the publicly available artifacts. So how do we actually verify and get guarantees about that? Okay, I think that's it. Next, please. Okay, these are the references. Next, please. So I would really like to acknowledge all the people who have helped in this. And yes,
so I'm going to suggest we might just take questions offline because
we can probably get it.
Okay, sure.
Well,
we can skip my talk. It'll be great.
It's okay. Thanks.
I haven't written them yet, but I don't need to.
No, I mean, yeah, we're over time.
We're over.
Okay. Yeah, thanks, but yeah, thank you. Who we got next up? Chris.
Chris. Okey-dokey. Stop slides. Start slides. Chris, where are your slides?
V3.
It is V3, yes.
I can do it on my phone. I requested.
Oh, you requested? Okay,
Yes.
excellent.
Granted.
Okay, let's get going. Oh, geez. Oh, geez. Oh, no.
Do you want me to just take away
Well,
your
like,
part?
it's cut off. Look,
Okay, so let me.
you want to just run it?
Let me. See.
Well, it was cut off on my thing as well. I couldn't. Share slides. Share slides.
Okay, somebody's trying.
No, they're not there.
They were in.
Like, they're definitely in the meeting materials.
Okay, so maybe
I'll
we
try cryptographic protocols.
V3. Sorry, I kept finding issues.
The text is cut off. How do I know?
Just
24/7/25. There we go. This were the ones that uploaded later.
Yeah, the last one uploaded. It's good. All right, so
Oh,
you're
nice.
running the slides?
I can
Stephen?
give you control if you like.
Sure. Okay, so I'm very interested in like what this group is doing, and I think there are potentially a lot of good outcomes that could come from the expertise in this room. Since it started off, I've been kind of wondering to myself, what does usable formal methods mean? How am I going to use formal methods? I'm a pen and paper person. I don't have any expertise in formal methods. The answer I keep coming into is I don't want to have to learn them, but I'm going to find a friend who can help me prove the things that I need help proving. But what am I going to have them prove? So that's the question I've been trying to answer. So this is an idea basically about how we should be writing security proofs for cryptographic protocols. And I want to kind of just constrain things to IETF because that's where we are. Okay, so the problem to solve is the following. We develop protocols that depend on pen and paper proofs that are relatively easy to generate, but are very hard for humans to verify and basically impossible for computers to verify. So the problem this creates is our demand for provable security may one day outpace the capacity of reviewers to actually check them carefully. And I think this is being driven by two factors. One, we're doing more with cryptography today than we've ever done before. We're not just looking at authenticated key exchange, we're looking at lots of different fancy protocols that do fancy new things beyond this. And we're also modeling attackers in greater detail. So that means we want to rule out larger classes of attacks. This requires us to model the execution environment in which the attacker is operating in greater detail. And what this means is we have more proofs to check, and the proofs themselves are getting longer. And this puts pressures, one thing this does is put pressure on people writing papers for conferences to either just sketch the proof for their security protocol or punt it entirely to the appendix of the paper. And I'm going to say the quiet part out loud. These don't often get actually checked because reviewers are not required to check them in most cases. So how do we solve this problem? I think we all believe that mechanization can help reduce burden on human reviewers. And what I mean broadly is having a computer, delegating to a computer, at least in part, the process of checking the proof. But this requires expertise in formal methods today. We have to, in order to write a proof that is formally verifiable, you have to know how to use the tools. So I just want to say this risk is not, it's not really hypothetical. There are examples in the literature and in standards of bugs in security proofs that were invalidated later, sometimes by an attack. So I want to pick on a particular class of proofs called game playing. Mainly this is because I'm just familiar with them. There are other kind of proof paradigms that are worth talking about here. Mainly, but we're focused on like computational security properties. So if Diffie-Hellman, my Diffie-Hellman group is secure, then when I instantiate TLS with it, so is TLS. That's the sort of thing we want to prove. So we model the security of the protocol as a game that's played by the adversary. So this game, we imagine running an experiment in which the adversary has Oracle access to the game, and it's messing around with the game state. And then at the end of the experiment, we measure some outcome, and we ask what is the probability of the adversary in winning the game. And what a proof does is relate that probability to the hardness of some underlying hard problems, like cracking AES or solving discrete logarithms, things like this. So the proof strategy is I think, conceptually easy to understand. We have our real security game, and what we want to prove is that this game is computationally indistinguishable from some ideal game in which the adversary has no hope of winning. So basically, what this says is any attack against the real system implies an attack against the ideal system, which by definition, you can't attack. So How does this look in practice? Well, proofs consist basically of a sequence of games, starting with the real game and ending up with the ideal game. And each of these games, we think of them as just computer programs like code. And we imagine to obtain in each game, we're obtaining the game by modifying the code of the previous one. So game G1 we obtain by modifying the real game. G2 we obtain from modifying G1 and so on. And what we want to do is prove that each rewrite ends up in a game that is computationally indistinguishable from the original game. And when we compose all of these little claims together, we get the result that we were looking for. So mathematically, this is a perfectly sound paradigm, and it's pretty conceptually simple once you kind of gain the intuition for it. So how does it go wrong? Well, where it goes wrong in many cases is the code bit, the actual specification of the games, and making mistakes there. So to give you a sense of how mistakes can happen, I want to walk through like just a very trivial example of a game playing proof. So this is from Mike Roselek's Joy of Cryptography. It's an introductory textbook that's available online. It's a great way to kind of get into provable security in this paradigm in particular for the first time. So we're going to look at hybrid encryption, public key encryption. The way we define security under chosen plaintext attack is as follows. We have a game where the where we generate a key pair. We give the attacker the public key, and then we give the attacker an encryption oracle. And it gives to this oracle 2 plaintexts, and we're going to encrypt one of these plaintexts. In the real game, we say we'll encrypt the left plaintext. And then in the ideal game, we'll encrypt the right plaintext. So just the only difference between these 2 games is which plaintext we're encrypting. So we say the public key encryption scheme is secure under chosen plaintext attack if no efficient adversary can distinguish between these two games. So let's look at a concrete construction. The idea here is very simple. We have a symmetric encryption scheme, a public key encryption scheme, and we're going to compose them in the following way. To encrypt something, we're going to generate a symmetric encryption key, call it TK for temporary key. We're going to wrap this key with the public key of the recipient to get a string called cpub. And then we're going to encrypt the actual plaintext with the temporary key to get this thing called csim. And that's our ciphertext is cpub plus csim. And decrypting is hopefully obvious to folks. You take the receiver's secret key and unwrap the temporary key and then decrypt the ciphertext with the temporary key. So this is the thing that we want to prove is secure under chosen plaintext attack. And we're going to reduce to the CPA security of both the symmetric scheme and the public scheme. So that is, if both of these things, the constituent parts of this algorithm are CPA secure, then so is the hybrid construction. So how do we do this? So here's our starting point. This is G1. We've obtained it from the real game by just inlining some of the encryption, the call to the encryption algorithm. So you can see the steps that we saw on the previous slide: generate TK, generate cpub, and then generate csim. And so our first job as reviewers of this proof is ask ourselves: is the real game indistinguishable from G1? And in this case, it's pretty simple. You can see we're still encrypting the left ciphertext, and we're doing the same exact thing. Just by inspection, it's easy to convince ourselves that, yes, these 2 games are indistinguishable. Okay, where do we go from here? Well, our goal is that we want to replace ML on the 3rd line there of the challenge oracle with MR. And we can't do that immediately because the outputs depend on ML. So, and we also can't appeal directly to the CPA security of the symmetric scheme because the key that's used, we're generating the key in the experiment. So what do we do next? The next step is to generate a new temporary key. And and use that to produce CPUBs so that we end up with CPUB and CSEM being independent of one another. And what we can show is that distinguishing between G2 and this rewritten G2 and G1 reduces to breaking the CPA security of the public key encryption scheme. So this is the part that takes a little bit of mental gymnastics when reviewing a proof. You have, so Mike Roselek he has a very particular style in which he shows reductions. And once you get the hang of the style, it's kind of easy and intuitive to understand. But the job of the proof is to kind of convince you that this reduction is correct. But what does correctness mean? It's basically like, it's what you want to convince yourself is, if I have a distinguisher between G1 and G2, I can construct a distinguisher that plays the CPA game for the public scheme that gets advantage in breaking the thing whenever the G1, G2 distinguisher gets advantage. So I'm not going to try to instill that intuition upon you, but that's the job of the reviewer. And then we have a very similar thing for the next step, where we actually replace ML with MR. And here we're appealing to the CPA security of the symmetric scheme this time. And it's a similar kind of reductionist style argument, very similar in fact. But it's, it's so similar that Mike, omitted this part of the proof. He didn't list the game in full detail, right? And similar for the next step, and this is totally like, it's not in there at all. It just says, just do the steps you did before in reverse. It literally says that. It's a textbook, it's fine. It's for people learning. But yeah, in any case, it's left to reader to kind of figure out this next step, which is you need to use the CPA security of the public scheme one more time in order to get back to the code that we had before. But this time we're encrypting the right plain text instead of the left plain text. Okay, so I don't totally expect everyone to understand that, but I want to take away kind of two main things. One is, this is a simple example, but it's very common for papers in the literature to skip steps because it seems trivial. And that's fine, I think, for an example like this, because it's for learning, it's pretty low stakes, but when we're talking about a real protocol that gets very complicated, the details, it's easy to make mistakes in all of the details. I also wanted to talk quickly about Mike's style here, which I think is really pretty. Does everyone follow the style? No, they don't. This is very suitable for this textbook. But in this textbook, we're not going to necessarily be using every technique that's available to us, every proof technique. And there's also the question of how complex is the problem space? So what you find in the literature is lots of different sets of conventions for pseudocode. And these are sometimes, the sophistication of the pseudocode kind of depends on the application, but it's also just kind of a matter of taste of the authors. And you'll see, if you look at one of your favorite cryptographers, if you look at their papers over time and you see how their pseudocode changed, I think it's really, you can get a lot of insight about what's going on in their life, I think, through that process. So I think we need to change the way we write proofs. It's obvious to me that the proofs that we write need to be immediately amenable to mechanized verification. And I'll say more precisely what I mean in the next slide. I also think that generating these proofs should not be harder than pen and paper. I shouldn't have to learn formal methods. I know that's a controversial thing. Maybe that's not going to turn out to be true, but I think that a separation of concerns is one way to make formal methods more usable. We focus communities on different problems. On the one hand, you have a subject matter who's generating a proof, who understands the domain, who understands how to design protocols in that space. And their artifacts are something that can be consumed by someone who's an expert in formal methods, who verifies the proof, whose job is more narrowly focused and doesn't necessarily need domain expertise in order to contribute positively to the work. I think this sort of thing is what we need to have, just more productive interactions across communities and across disciplines that are just culturally kind of different. So I think the solution is quite simple, and I don't think this is the first time this has been proposed, but proofs should be software. Protocol specifications and security definitions, and then each of these game transitions that kind of make up the bulk of the proof, this should be written in code. First, I guess I messed up the order here. I wanted to give a flavor of like what formal methods people would actually be doing. They're verifying claims like this. So we have the, we're looking, what is the probability? So we quantify overall adversaries and we say, what is the probability that an adversary, that when we run the adversary with some experiment, we observe some outcome. And we, in different steps of our proofs, we're looking at, we want to say that, the probability distribution is the same. And this comes up in a lot of different kind of rewrites that we see in proofs. So some requirements that I would add for the programming language we pick would be, it should be popular. It should be something that people actually use. So I'm not saying I don't think Coq is appropriate. I don't think F* is appropriate. I think a high-level programming language that is likely to be used by a lot of people. It should be readable. One should be able to understand the protocol without having to know the semantics of the language. And it should be deployable. This is a bonus, but I think it's going to be important. No translation. There should be immediate translation from the developing the specification to actually code you can deploy and run. And that's, I think, most important for work at IETF. So why not Rust? So I think there's a few reasons for this, pros for this. It's widely used at IETF. It's used in production software. Cryptographers love it because it solves a lot of the problems that we don't want to have to solve ourselves. But that's just the software engineering side. There's also, I don't know all of the tooling around here. I don't know. This is coming from a very narrow band of experience. And I'm happy to have a discussion about whether this is right or wrong. There is this HAX toolchain being developed by Crispin. It translates to different backends where you could do formal analysis. It's used today to produce formally verified implementations of standardized cryptographic algorithms. So MLChem being kind of the most famous recent example. They also have a formally verified or formally verifiable, let's say, implementation of TLS 1.3. So cons to this, we can talk about how readable Rust is compared to other languages. For example, CFRG commonly uses Python for specifications. I think my impression is that Rust is easier from a tooling formal methods perspective. Could be wrong about that. But yeah, that's it. So I think the outcome that I'm hoping for is for formal methods people who don't necessarily know about cryptography. I would love to see what you think of this problem. I have some concrete examples that kind of illustrate the different sort of rewrites that we need to think about. And I think basically this is the thing I want you to go prove. And if it works, it works. But thank you very much for your attention.
Yeah.
So I sort of like the idea you're proposing, but I'm pretty sure it's like the empty set in the middle. I mean, when I hung out with functional programmers, the people who really do these formal proof stuff, they are just different human beings. We're dealing with something that is on the edge of NP complete stuff.
Yes.
And mere mortals that can just read something in Python don't get to that altitude that they're at.
Yes.
Right? This is like climbing to the top of Everest without oxygen tanks. I would like to go, but not happening. Right? So I think you're constraining the situation there. I think we need to get people who can do formal proof stuff working with people in the teams, but I don't think you'll get the scale you're looking for if you choose something that is you know, if you're trying to do stuff that everybody can use, because I just don't think this is going to work in my lifetime.
So Hacks is doing some interesting things. I totally don't have a full. I think like I have an intuition for what you're saying. Like the problem that I'm pointing to is very, very, very hard. People are doing very sophisticated things with Hacks. I think I don't know if this problem is solvable by Hacks. If we could prove claims like this. Yeah, I don't know if this is the thing that like if there's something technical if there's something about this, I want to understand how hard this is basically. I think it is definitely different than what people are doing with Hacks. This isn't a use case people have envisioned for this specifically, but if we can do it, it'd be great. Yeah, I don't know. You're probably right.
Well, I do hang around at other conferences. I've seen folks that are doing formal logic proof stuff, and they'll look at something on the page and they go, "Oh, line 76 is wrong," and I look at it, it's just set theory stuff that I'm going, I have no idea how you A, even read that, and B, figured that it was false, right? I mean, and this is a skill set that folks in this community just do not have. And by whatever mechanisms, I can't imagine that you can get that transplant out. So somehow I think you need to meld humans together, but I don't think the individual people here will be able to get that. Anyway, okay.
Yeah, so
we're
running quite low on time here.
I'd love to be proven wrong.
I'll do my best to prove you wrong. Thank you.
So we're over time. So if you can be very, very brief, that'd be good. Thanks.
Sure. Leonard from ETH Zurich here. Thanks a lot for this very inspiring talk. I think this is mostly a clarifying question. I was wondering about the deployable part that you showed in the diagram towards the end. Are we talking here about a deployable implementation that acts like as a horrible, inefficient reference implementation, or do we want to have a formally verified library that we can deploy that people actually want to put into their products because it is actually fast TLS?
That's a very good question. So my expectation is that the reference implementation should be as clear and as simple as possible without necessarily optimizations. But if you start with like Rust code, then or Go code or C code or whatever language we pick, and optimize from there, I just feel like the gap between the thing that you know and the thing that you don't know is smaller and more constrained or constrainable, let's say. So it doesn't mean like we're going to stick Birdie one. I think it's called Birdie. So there's a Rust implementation of TLS 1.3 called Birdie that is formally you can transcribe it to F* from Rust using Hacks. Anyway, I think it's probably efficient enough, but yeah.
Felix, it's very quick. Yeah.
Yeah.
And Deirdre, sorry, the queue is closed. We're too short of time.
Hi, I'm Felix. I just wanted to utter a remark from my gut feeling. So I understood your motivation of the presentation as we often have problems in checking proofs, but generating them, not so big of a problem. And I was like you basically draw the line of we have the engineers that can also generate proofs, and then we have the formal methods people who check these proofs. And in my experience, coming from the Tamron world, that is not really how I experience the world. I often find that engineers even struggle with writing down a concise threat model or the security properties they want to actually achieve. They have a good intuition for them, but if you even struggle to write down a security property, I think you'd also struggle to write a proof.
The person I have in mind is a provable security person who is also a software engineer.
Thanks.
So it is two skills.
So again, sorry for cutting people off, but we're a bit short of time. So Robert, I can give you control of the slides. Thank you. Yes.
Thank you. Is the sound good?
Sound is good. So you should have control of the slides. Could you do
Great,
it?
yeah.
Can we? We're in short of time. If you could do it in like 10 minutes, that would be super good. I don't know if that's possible.
Oh God.
78 slides.
All right. I try my best. Yeah, I wanted to
Oh,
start.
sorry, Robert, before you start, I think we had planned to have Francois just give a little advertisement for some work that's happening with SSH, hopefully. Francois, I don't think we'll have time for slides, but basically there's some work, hopefully restarting on SSH. Some formal methods work on that could be good. And I think that was Francois's 4 slides. So forgive me for, yeah, okay, thanks. Okay, now Robert, go ahead.
No
You have
worries.
the rest of the time.
All right, okay. So this is about specifying protocols, and I will quickly talk about my biases because there's many people in the group that are doing format analysis of software and so on. So I'm doing security protocols usually, things like TLS, WPA2, things that are a bit less like this, like OCSP stapling and PKCS11. But I do work with the 2 predominant tools in this domain, Tamar and ProVerif, and to sort of fix the domain. The specificities are that they are theorem provers specifically for security. So they include by default a $Yao attacker, which is an attacker that assumes perfect cryptography but allows mangling messages that are being sent on the network. It also targets unbounded sessions that which would sort of contrast with Ben Greenan's model checking approach, where you try to look for small examples, right? Where he sort of the state of the art is to look for unbounded sessions, but only for protocols, not as general. Where we don't have decidability, so the tools tend to work well with how protocols usually look like, but we can also prove that they won't work on any protocol, and that we focus on safety properties. These are things like authenticity or secrecy. Basically, things can go where you can see it goes wrong from a single run of the protocol. What I'm missing here is things that you would use general purpose verifiers for, like proving functional correctness, the verification of the implementation using program verification, properties that are specific to low-level protocols on the network level, and liveness properties. So this means that you don't get stuck. That's a property, for example, resistance against DDoS attacks, right? So within this domain, we are doing, as usual, informal verification. We have a system and we prove a property about this. A system could be a protocol, and the property is a safety property. Okay, but where does it come from? We read RFCs, and then we sort of solve the non-determinism that Usama talked about, and create a mathematical model from it, and then we verify this model. And I want to talk about which language might be good for this, and what these languages are currently missing. So the 2 languages are defined by the 2 predominant tools in this domain, which is the Tamar Improver and ProVerif. And I try to be quick in going over how they look like. Okay, so we have a protocol, and we'll only show you the initiator, the role that sends the first message. In Tamar, you define rules for every step, where a step is defined by first checking that certain facts are in your current state. In this case, there's a special fact that says some ephemeral key is fresh, and then there's a part of your protocol, a fact established by your protocol. We will see the rule that generates it in a second, that says there's a long-term key identified with the initiator, and then these rules rewrite the state. They remove what's on the left-hand side, unless it has this exclamation mark, and then introduce a new fact. So we would introduce a fact that says we're in this new state, and that we want to send a message out. Right, and then if the initiator has a second step, it has to start from the previous state. Usually it reacts to some input doing so. So if it is in the previous state and gets some input, then it does some verification thing. So these are actions, that's the stuff that's in the middle, and establishes a session key. And the empty set is what we substitute with, meaning that everything on the left-hand side is removed. Okay, and also setup is no different from the specification of what the parties do. So the setup, the thing that says this party has this long-term key, means that we take for a fact that this is a fresh key, not used before, and we establish that party A, for example, has the specific long-term key. Okay. contrasting this with ProVerif, we have a process calculus. So this is the other way of modeling protocols that's predominant in the academic literature, where the blue rule on the left-hand side corresponds to the first part of the process, which says you create a new key, you output something. It's the same output as on the left-hand side. And then the green part is the second rule, right? So the continuation indicated by this fact init1 would be displayed as just a sequential composition using the semicolon, like in C, and just going into the next line. And likewise, the setup of the whole system is done in a process. Okay, so these are the two ways. When we look more closely into the RFC, we see though that there's something missing. So this is the RFC of WireGuard, the VPN protocol, and we see that we can pretty clearly get the message flow and the setup of the RFC reflected in the model. What we observe though is much of the RFCs is concerned with message formats. This is the message that the initiator actually sends, and we have to tell the implementer how many bytes have to be reserved for the type of the message, how many bytes we reserve for future applications, and so on. That's something that an implementer needs. This is often abstracted by us. So we say just everything that goes into there, the identity of the party, the identity of the intended responder, and the actual cryptographic message and the signature on them, they just go into a tuple. That's the angle brackets. And we noticed this particular in a project that we've been working on, which is for monitoring implementations for specifications. So we had in the earlier talk the discussion of whether you want to have a reference implementation or a very fast implementation and so on. So if you have a very fast one, you want an easy way to check whether it adheres to a specification. And this is one way to do it. So the idea of this specification monitor is that you have a fast protocol implementation and you observe the network output using whatever system it runs in by observing system calls or something like that. You also observe the call it makes to a cryptographic library. If you know the cryptographic library that is, if you choose a popular one, you have a good chance that you find applications that do this. And you generate a stream of events that completely captures the behavior of this implementation. And now this specific tool monitors if this is a possible outcome of executing the specification. And while we were doing this, we noticed that we need the format strings inside the specification that is usually used for verification in order to really understand the messages that we receive. Okay, so we had to develop message format language that we integrated with Tamarin. It contains function symbols for typing things as integers, bytes, or strings, which in the view of the verifier are ignored because it doesn't need it. Concatenation and logical operations that are abstracted by just keeping everything in pairs, basically as was done before. And function symbols for reversing things to adapt from big little endian to little endian order, and also addition, because we often have counters in protocols. Okay, and this again is the snippet from the WireGuard specification, and this is how it would look like. I try to be quick about this, but we can basically describe the concrete types. The blue bit corresponds to the blue bit in the code, and describe the formats now. Okay, and this I think is potentially useful for specification purposes. This format can express the setup of parties. It can describe how parties react. This is basically what I showed in the second slides. And now, due to this addition, we have a way to also describe the message formats, which was not possible before. There's still some caveats when I think about how this should be done for RFCs in general, how I would imagine as a verification person idealize them. One problem is that when we use something like Tamarin, we have the facts and they are named, and there would need to be some standardization of this. For example, the first rule of the initiator should be called initiator start throughout the box. It might be attractive to look at proverb to this end because there is no explicit state unless you model really complicated state machines where you need to use other means of encoding them. A secondary use, besides the slight addition to the existing languages for describing protocols, is that SpecMon allows us to validate the spec against the implementation. And you might say, we don't really care for this, right? Because we usually specify things before we implement them. But is it really true, though? Isn't it that we often have implementations that we base the specification on? And isn't it also this case that the specs do in fact contain errors when implementers start implementing based on them? We have talked before about underspecification. That's not so rare. Sometimes they have errors. That's not so often, but underspecification, I think a good part of the audience probably has experience with this kind of observation. The other big advantage for me, is that verification with Tamarin would be possible, similar to the HackSpec framework. What about ProVerif? We have some work on progress that translates Tamarin to ProVerif that could help, but and there's also tools that translate from a third language into Tamarin ProVerif, so you could use that. The message formats, though, the idea is not very tied to Tamarin in particular and could be integrated into other languages. Okay, so we try to see if this works in practice with the WireGuard protocol, the VPN protocol. It's how I connect to my workplace when I'm in home office. And we found the following differences between an original model put out by the authors of the protocol on the website, which they used to prove it in Tamarin, which is excellent that they did this, right? And we adapted this model to bring it to the point where we can monitor the reference implementation to see what the difference are. So what is the difference between a model meant for proving things and a model good enough to actually monitor the outputs of an implementation? And we found that the message formats are necessary. We can't get around it because otherwise we can't interpret the messages. We have to know in which order they are, how long they are. We have to be able to do parsing. We also found that the model doesn't talk about how long-term keys are established. In reality, in the implementation, they are stored persistently in a configuration file. And we need to express this step in the model again. So this is something that is also, we also looked as a third category into the RFC. The RFC has the message formats, of course, but not how exactly long-term keys come to play, right? Then we found that there's a difference between how the implementation computes values and how the model assumes this is taking place, or how the RFC would specify this. When the implementation gets, so we wanted to check for performance. So we had tons of clients, tons of servers communicating, and we found out that the implementation, if this happens, opens a bunch of workers that run in parallel to really increase the throughput. And that necessitates that some of the pre-computation takes place before the worker is spawned and some afterwards. And we found that neither the model nor the RFC are representing this. I'm not sure if they should, but it is basically something where the implementer makes a choice that is potentially relevant for security, but is on their own.
Sorry, Robert, just to let you know, we're down to about a minute to go. So.
Okay, all right. So you can check the slides if you care for the differences in total. Yeah. So the conclusion, the takeaway message is for protocol specifications, message formats are important, and we added them to Tamarin, and we could add them to ProVerif. and make them more useful. Or make them useful. Maybe that's enough, right? As an extra, it also permits monitoring, which might be a very easy way to double check the specification if it's realistic enough. Yeah, and I think this might open up some questions that I think I would just put out here if I'm out of time. Yeah, maybe you guys have some comments on these questions.
Sure. So I guess we're about 30 seconds away, but let's have a quick question. May as well use the time while we have it.
Okay, very quick. So what's your plan for ProVerif? If I understood you correctly, you are saying that you have for Tamarin, but not yet for ProVerif. Is it correct? And if yes, then
Yeah.
what's your plan for ProVerif? Like the problems I showed would be very nice to have such a tool. I find it very, I think that will be very helpful and useful.
I didn't have any plans to do it, but if there's demand for it, that might be a reason to do it. Right now, the monitor does. It might make sense to integrate this into Cepic Plus, which translates to both tools, and then have this as an intermediate layer. This could probably be the simplest way of doing this.
Leonard from ETH Zurich here. So very cool work. Congrats to this. So 2 quick questions. Where can I find more about this? Like, is this already published work? And the second question is, we didn't really talk about the monitor at all. And I was like wondering, given that we're dealing here with encrypted messages, how do you monitor that the bytes that go out to the network actually, I don't know, are like correspond to the bytes of a ciphertext where the right inputs were used according to the Tamarin model?
Yeah, that's true magic. No, we observed the cryptographic, the output of the cryptographic library. So we would see that this party is taking a message, it's encrypting it. We remember the bit string, we know the message format. So we want to see a certain bit string on the network next. And if we don't see it, we shut off communication. Of course, it's more complicated than that because we have non-determinism in protocols all the time and we have to account for this. But also the nice thing is protocols are usually very good in resolving it themselves. We just have to be able to do it if they fail.
Okay, thanks a lot.
And for where to get it, it's just been accepted at CCS. So come to CCS, see the talk of my student.
I will be there.
Great.
Okay, great. Thank you. Thanks everybody for coming along. Thanks to all our speakers. And unfortunately, we don't have time for Jonathan's talk. But yeah, so we're talking on the list about whether to organize some next steps and meetings and whatnot. So thanks all, and enjoy the rest of your IETF week.
So this is your coming plan, right? You just put yourself at the tail when you get 10